At example 4 from our transformation content. In this example, we were given the general form of a sinusoidal function, which is this kind of gross looking guy over here, what I've called f of x. The purpose of this general form, general sinusoidal trigonometric function, is that it's got our trigonometry function sine of x, but it's also had all 4 of our relevant transformations in general applied to it here, so that we can do anything, we can manipulate this sine function any way that we want. So my first question is, just looking at this sine function, can we determine which of the parameters a, w, t, and k are being controlled by each, are going to control each of our different transformations, vertical shift, vertical stretch, horizontal shift, horizontal stretch? So let's go ahead and talk our way through these. First of all, vertical shift. What I know about vertical shifts is that vertical adjustments are always going to be outside of the parentheses because vertical adjustments affect our y values, which are our outputs. So if the adjustment is an adjustment to the output, it should be outside of the parentheses of our function. So the sine function has its parentheses here. I know my adjustment should be outside of the sine function since we're affecting our outputs. I know that shifts are going to add or subtract amounts to our final output. So it looks like this k term is what's going to be adding and subtracting things here. In general, we write our vertical shifts as shifting things up or down by k units in general. So this vertical shift term will be k. If we come over here and we look at our graph, what we'll be able to see is that if we slide our slider bar around for k, we do indeed move our original function up or down by exactly the number of units that k has been shifted by. If I set k here to be 4, then we can see, there's 4, then we can see things like we used to go through the origin, now we've been shifted 4 units up. We used to have a maximum height of 1, we now have a maximum height of 5. So I can see that vertical shift happening there with k. I'll set k back to 0 for our next example. In this next one here, I'm looking for my vertical stretch term. Again, because the adjustment is a vertical adjustment, it should be adjusting our y values. Y values are our outputs, so I expect this adjustment to be occurring outside of the parentheses. When we stretch terms, we are making them multiple times taller or shorter, and the multiplicative adjustment that I see outside of the parentheses is our a term here. We generally write these as a times f of x. So in this case, the a term of our equation is going to control my vertical stretch. If we come over here to our a term slider bar, we can see that as we make it larger, our function gets multiple times further away from the x-axis. Notice here that we have made a4 in this example. We used to reach maximum heights of 1. We now reach maximum heights of 4. Minimum heights were at -1. Now minimum heights are at -4. Also notice that there are points that used to have a height of 0. Well, 4 times a height of 0 is still 0. So we're still exactly at a height of 0 here because 0 times 4, still 0 right there. But all of the heights of each of the points on our graph are now 4 times taller whenever I have a coefficient of 4 out front. Also notice that if we make a very small, if I make a 1/2, oh, there we go, 1/2. Then now all the heights of my red function are only 1/2 as tall as they were when they were on our original blue function right there. So A is controlling our multiplicative height transformation right here. Well, how many times taller will the graph be than its original? I'll go ahead and set A back to its standard value of 1 so that we can look at our next example here. Next up is horizontal shift. Because this transformation is horizontal, I know we're affecting our x values. X values are inputs, so I expect to see this transformation occurring inside of the parentheses of the sine function. Since I know it is a shift, I know that means that we are adding or subtracting amounts to our x value, and so I see this t term right here doing that for us. Generally, we've seen this, I'm going to write this with an h because I know that we've been seeing in our quadratic stuff x minus h squared. Generally, this is written as h for a general shift term here, but in terms of the parameters that we saw within this equation, we would think of this as t. If we come over here to see, watching this guy slide around right here, I do see that my function is sliding left and right. It looks like this is a left or right shift relative to the original graph that we started with. Notice very importantly here, I did write this function with a minus on the inside and a plus on the outside. This is exactly like we've seen vector form of quadratics where there's subtraction x minus h squared. and then addition plus k on the end. That's exactly what we're looking at. Because I built in this negative, that does mean that making t bigger does shift us to the right. But in general, we want to think that the opposite is always true for these internal adjustments. They always occur the opposite direction as we think. So here, t is really getting more and more negative as I make it get bigger, and that is shifting us to the right with the subtraction there. Shifting us to the left happens with addition. Here we are subtracting a negative value. So this is really like x plus 3.3 is resulting in the shift left by 3.3. So over here, we've got our answer there. Our horizontal stretch is our last term. Since it is horizontal, it affects our x values. X values are inside the parentheses. Since it is a stretch, I expect it to be a multiplicative transformation. So I see that w, or what we really actually call as omega here, is going to be our stretch term. So f of wx here, w is what's doing our horizontal stretching. And again, we want to remember that all of our transformations that are inside the parentheses are always going to happen the opposite of how we expect them to happen. So here, for example, as I make my w get larger, when we see that w goes to a value of 2, for example, rather than seeing this graph being twice as wide, we'll see it be only half as wide. Our input is going to get doubled before the function is applied, so we can get away with contributing only half as much to the function if we have sine of 2x as then compared to when we had sine of just 1x. So a little bit tougher to see when we have both the graphs on here. I'll turn off our original, but what we can see is that this graph has now been kind of squashed by a factor of 2. It used to be quite a bit wider, and so maybe now what we can see is we used to have a peak at pi halves for our first peak, but when we make this w go to 2, we now are only at pi fourths. We only had to go half as far with our input because our input was going to get doubled before the sine function was applied. The larger and larger we make w, the more and more scrunched up this should get. This should only be 1/10 as wide as the previous graph there. We can see we were at a peak at pi over 2. We are now at a peak at pi over 20. It only took 1/10 the input to get to the same heights as we used to experience here. We'll return this to a height of 1 here, and we can turn back on our blue function as well here. These should be in the exact same location now. So now that we've seen which parameters control which equation, we can go ahead and verbally compare these two equations. We were asked to compare sine of x to 3 sine of 2x plus 1. One of the important things I do want to do here is, rather than just listing what I think I see from the three transformations, I'm going to make sure that I list them in the order that I know that they would occur in relative to the order of operations. The order of operations, which we know as GEMDOS, is going to say, first, do all the operations within the grouping symbol. So the first transformation that I see is going to be the 2x term right here. What the 2x term for me is going to do, we just saw a moment ago, this is like our w term. Whenever we have the 2 as the coefficient here, this says we can contribute only half as much x, and we'll get the same result because our contribution of x will get doubled before the sine function is applied. So this should just make us half as wide. This is going to compress us by a factor of 2. The next one that I see here is we've got that coefficient out front of 3. I'll say a equals 3 in this case. When I see this a equals 3, this says to me the outputs from my sine function are now going to be 3 times as extreme as they were before, 3 times as far away from the x-axis. If before we reached maximum heights of 1, then we'll now reach maximum heights of 3. So this should make us 3 times taller. This should be a vertical stretch of a factor of 3. Finally, we'll see here that on the end, it looks like we have a k value of 1. And we have a k value of 1, this is going to tell me, take all the outputs that you were getting from 3 sine of 2x and add 1 to all of those outputs. That should vertically shift us up by 1. So let's go ahead and do each of these transformations in order over here, and we'll see each of these things happen. So first things first, we need to make our w term 2. We're predicting that this makes us half as wide. And so we can see here, it used to take us until pi halves to get to our maximum. It now only takes us until pi fourths to get to our maximum. It only took us half as much input to achieve the same result of reaching our maximum height. Next, we want to make our graph 3 times taller by adjusting our a value to be 3. This is going to vertically stretch all of our points to be 3 times taller than they used to be. So now that a is 3, you can see that our graph used to have a maximum and minimum of -1 and 1. We now have a maximum and minimum of +3 and -3. Finally, we are going to vertically shift our graph up by 1 by making our k value 1. So as I slide k, I expect the entire red graph to shift up by 1. And we see that we've moved up. Now instead of going from -3 to 3, we go from -2 to 4. Our minimum and maximum values and all the values in between have all been increased by 1. Finally, let's go ahead and take a look at this last function here. For this one, I'm going to want to zoom out a little bit, and I'm going to return my red graph back to its original settings here of 1 and 1 for the multiplicative adjustments, 0 and 0 for the additive adjustments here. So for our last problem here, I'm suggesting to you that we've been currently given some sinusoidal function that has a capital A of 4, an amplitude of 4 is what we say in trigonometry. So what I know about an amplitude of 4 is that this is going to result in our graph being 4 times further away from the x-axis than it originally was. We have a vertical stretch factor of 4. If I change this to a vertical stretch factor of 20, then how can I verbally describe the impact that this will have on the graph? Well, one thing I can do is I can go ahead and zoom out here. I know that if I set my a value to 20, then I expect my heights on my graph to get to a height of 20. I could set my a here to 20, and I can see that we get this really extreme vertical up and down action right here. It looks like we are getting to maximums and minimums of +20 and -20 here. And so if I want to verbally describe what transition I made here, well, I can think about what this graph might have looked like. Before, we had something that looked like 4 sine of x, and if I want to make this look like 20 sine of x, then what am I going to do to modify this to get to 20 sine of x? Maybe I'll write this like this here, 20 sine x. Well, what I need to do is I need to multiply this entire function on the outside by 5. If we multiply a function by 5, what we've learned in this unit is that multiplying by 5 on the outside should be a vertical stretch of 5. So I'm going to think of this as 5 times 4 sine x. That's how we get to 20x here. And so I would describe this as a vertical stretch with a factor of 5. It's now 5 times taller than it was. To show this, maybe I'll get rid of these graphs here and just show the two graphs that we're interested in right here. We are now comparing sine of x, we're now comparing 4 sine of x to 20 sine of x. And in this case, what we can see is it seems like these graphs are doing similar things. They cross the x-axis at all the same places. The only difference is that when this graph reaches a height of 4 at pi halves, this graph instead reaches a height of 20 at pi halves. It is 5 times vertically stretched relative to the smaller of the two graphs here. So when we changed a from 4 to 20, we performed a vertical stretch with a factor of 5. The graph is now 5 times taller than it used to be. If you have any other questions about this, you should just go ahead and let me know. Thanks.